In this video, we're going to look at lines and planes in space. We have three goals. We're going to look at how to write a set of parametric equations for a line and also their symmetric equations. How to write a linear equation to represent a plane in space, and then how to sketch that plane once we have the equation. Finding distances between points, planes, and lines will be done in a separate video. Lines in space. If we're looking for a line that's going through a given point that is still parallel to a vector, we can use the vector to help us guide the direction so that we can maintain line L being parallel to the vector. The point provided that the one that you specifically want to go to is going to be labeled x sub 1, y sub 1, z sub 1. So this is the point that you want to be going through. And the ABC from the direction vector, so that it can stay parallel, will provide the direction number. So that's going to tell you how to move along the x, y, and z axis in order to still keep that distance away from the vector and make sure that L is going to be parallel to vector v. What it goes through, that second point, is going to be Q. But there are going to be multiple Q's because a vector has an initial point, which in this case will be P, but multiple Q's, and every time I extend that terminal point, it's another vector. But all of those vectors will be parallel to V. And so those are going to be scalars. That ray PQ will be all scalar multiples of V. And T is going to be our scalar, and that's where the idea of the parametric equations come in. You're going to set up a parametric equation for each coordinate. So the Q point will have an x coordinate that starts at x sub 1 and that moves however many times you want at the same direction as the vector which was given by the a value. And then it will do the same thing for y and z. So x will start at p sub 1, move the same way in the same direction as a. Y will start at y sub 1, move the same way in the same direction as b. And then, of course, z will do the same thing, starting at z1, moving using the c value from the direction vector. When we have it where x, y, and z are equal to an expression, those are our parametrics. When you rewrite it where each one is set equal to t, well, if each of them is t, then they're equal to each other, and those are going to be your symmetric equations, right? Because that's going to be that end point, that Q point that you plug in, and it will tell you the t value that you use, like how many times did you extend that line using that same amount of steps. Let's look at an example. I want to find the parametric and symmetric equations of the line L that passes through the point 1, negative 2, 4. So that's P, that's where we're going to start. We want it to be parallel to the direction vector 2, 4, negative 4. So what, or which, I should say, Q's do we need to stop at? Well, I'm going to pull out x1, y1, and z1, and then I'll also pull out a, b, and c. And then from that, all we really need to do is plug it into those parametric formulas. So x will be equal to 1 plus a 2t. Y will be equal to negative 2 plus 4t, and then z, the 4, the z1 point, and then it was a negative for the last value, for the c value, minus 4t, and those are my parametrics. And then you can extend that line as long as you want it to be and push that Q out and make it as far out or as close as you want to the P value. If we rewrite each one of these equations for T, we get the symmetrics. So I would just subtract over the constant. So I have x sub 1, and then, of course, divide off your coefficient of t. And for each one of those, since they'll each be equal to t, then they can all be set equal to each other. And that is how you can find a set of parametric equations to come up with a endpoint, a Q, for your vector, your line that will be parallel to the vector v. Let's look at an example from WebAssign. I have the point negative 509, and I want to be parallel to 7, 9, negative 2. And so I have A is a 7, B is a 9, and C is a -2. And of course, this is my point, so that's my X, Y, and Z sub 1, since that's where I want to start. And so my parametric equations will just be X equals, start at my X sub 1, which is a -5, move as many times as I want using A, and that's how I would get to the X part of my Q coordinate. Do the same thing for Y. I have a 0, so I just won't put that in. I have 9t. And then Z would be a 9 minus 2t. And these are my parametric equations. So if I say I want this to be a length, just the one step further out, think if you can kind of think about slope and repeating that slope, you only want to go once, then you would put in a 1 and you would get a Q value. You want to make it twice as long as that, so times 2, and so this would be 14 plus the 5. Let's find our symmetrics. Well, if I add over the 5 and then divide everybody by 7, I get X plus 5 over 7, and so I must be looking at this last one. Of course, here I would divide by 9. Here I would subtract the 9 and divide by the -2. They divided the negative away, so they flipped the symbol, but you can certainly leave it as Z minus 9 over the -2, and that's completely fine. And that's all that there is to it. If you have a point and a vector, it's kind of the same as having a point and a line, and you use that to find the rest of your information. Planes in space are going to be a little bit more involved because we're going to have multiple points and we're going to need multiple vectors. So if I have a point that is on a plane and I have some normal vector that's being created, now normal vectors will always use the n, and so that will also be an ABC. How do you know when it's a normal as opposed to just a regular vector? If it's a normal vector, they'll always use that bold n. Now this plane has all the points for the Q value that you would have to stop at in order so that vector PQ, that line PQ, is orthogonal to n. Since n will always be orthogonal to PQ, doesn't matter where Q is, pick your favorite spot and draw a different Q. All of these little Q's that are on here are orthogonal to n. That means wherever that Q is, where PQ anywhere, when you dot that with n, it's going to be a 0 because the angle between them has to be a 90-degree angle. We're going to use that to help us set up our standard form. Take your normal vector, dot it with PQ, but of course, we're not going to know Q. We're just going to have an initial point P, some point that's on the plane. And then we want to find out the extent of that plane using this formula. Now we know n is going to be ABC. That will be either given or able to be found through an equation of a plane. And then we're going to use the very similar ones that we use for the parametric. And when we dot, we'll have something that looks like this. Find the general equation of the plane that contains these points. All right, so now this time we didn't get a vector. They didn't tell us a plane, but what they did is give us 3 separate points. So what I can do is find out what the vector between this one is. I'll make this PQ and I will make this P1, Q1. And then I can find the normal vector between them. So let's find out what our points are here. And we're going to make this U and that V, and then we'll be able to find these vectors. So U is going to be a -2, 3, 0. And then V will be a -4, 0, 3. So all we need to do is find those position vectors. Once you have the two vectors, you can find a normal vector to any two collinear, right, one that shares a point, vectors by finding the cross product. So now we're going to cross u with v, and that's going to give us the normal vector. That's what a cross product does. It gives you the normal vector. So we'll place that in there. However you want to go through the process of finding the normal vector, I like to cross out this top line and then work my way through finding the three single determinants. And let's go ahead and write it out. That would be a I hat, and then when I cross out this line, I would be left with 3, 0, 0, 3. Negate the next for j hat. I would cross out the j column. I get negative 2, 0. It looks like a 20, but it's a negative 2, 0, and then a 3. And then keep the sign on my last one, and I would cross that out, and I get negative 2, 3, negative 4, 0. And now I can find each one of these. So pretty easily, you see you have a 9 there. This would be negative 6 minus a 0. So I wind up with a positive 6, and there we go. And we have our normal vector. And so my normal vector gives me my direction, and that's A, B, and C. Well, now that I have my point, and I have A, B, and C, I can go ahead and substitute everybody in. And then it's just a matter of cleaning everything up. Distribute and combine some like terms. And now you have the general form. If you're given the normal vector, it saves you the time of having to find the cross product. Or if you're given an equation of the plane that you are looking to work with, then you also know the normal vector because you'll be able to just pull out the A, B, C values. You can find the angle between two planes in the very similar way of finding the angle between two vectors, except now you'll, instead of using just dots between the vectors that we'll have to use will be the normal vectors for each one of those planes. You know how to find a dot product and a magnitude, and so it's the very same process. Let's sketch instead of finding angles between. To sketch planes, you're going to use the intercepts. So if you're looking for an x-intercept, y and z will be 0. If you're looking for a y-intercept, x and z will be 0. The same way we did all the way back in Algebra 1. You're going to use a trace. So I have the equation of the plane, and you can trace each one at a given time. So you can find out what this line looks like, and then you can find out what the YZ trace looks like, and then what the XZ trace looks like, and put those lines together. I like to just find the intercepts because you'll wind up with the same thing. And then you can extend your planes. Let's look at one in WebAssign. Go to WebAssign, and I'm going to scroll towards the end of the homework that is assigned for this class. And there it is. And I have sketched this plane. So you can sketch the individual planes for the XY, the YZ, and the XZ. But I kind of cheat a little bit. And I would just say, well, what would this x-intercept be? I have 4x, if this was a 0 and this was a 0, equal to 56. And then I could just go ahead and divide 56 by 4. And I get a 14. So it looks like it's right about there. It's certainly not here. Maybe there. Not there. So it looks like that might be a 14. Now do the same thing for y. So 2y is equal to 56, so that would be a 28. So it certainly looks like it has to be this one, so I would connect that line. And then if you finished up with z, you would see that z has to be 8, and I have this little sketch here. Now you would extend this plane. It wouldn't just be this little triangle, but I would use the triangle to find the rest of that plane. And you can see later on, they actually even just ask for the intercepts and not just the full line. So you can find the full trace by sketching the line and then piecing that together, or you can just use the intercepts. So sketching the 3D plane, it looks a little awkward because it's hard to sketch 3D on a 2D plane, but it's not terribly difficult to do. It uses the same ideas. If you're looking for things that are parallel, if I want my plane to be parallel, the purple plane to be parallel, to the YZ plane, then you can see that it's only going to be going through this X1 intercept over here to be the only intercept. So the plane that you're going through, the one that is missing from what you are parallel to, that's where your intercept's going to be. So if you're parallel to YZ, you're going through X. If you're parallel to XZ, you're going through Y. If you're parallel to XY, then you're going to Z. In the next video, we'll look at how to find distances between points, planes, and lines.